Hello viewers, welcome back to our series of lectures on NMR spectroscopy. Today we will continue our discussion on the basic aspect of NMR spectroscopy. We want to learn about NMR as a phenomenon to begin with. NMR, you know, is nuclear magnetic resonance. So far we have touched upon the nuclear and the magnetic aspect to some extent, and today we will continue to talk something about the magnetic aspect of it, and then we will understand what is the meaning of resonance in NMR. So, that is the way we are going to go about today. The session is planned as follows. That is, to begin with, we will try to see what is the story so far, where have we reached so far. We will try to recall what we have done in the previous session. Thereafter, we will learn about what is called as precessional motion, a consequence of putting the nuclei with I is equal to half into magnetic field. Having done that, we will then try to come to understanding what is the meaning of resonance in the context of NMR. Thereafter, we will learn about the relaxation mechanisms, the ones which are used to maintain the population difference between the two energy levels, and then towards the end we will try to sum up what we do today. Okay. Let's recall our story so far. What we did was, we have seen in the previous session that the nuclei with spin quantum number I is equal to half, typical examples being 1H, 13C, 15N and 19F, they are active in NMR. They are active in NMR because these are spherical nuclei which are spinning and have an associated angular momentum I, which is given by the following expression, and that is how do we represent that. Now, these nuclei which are spinning have an angular momentum, also have an associated magnetic moment mu. This magnetic moment mu is proportional to the angular momentum I, and these are the kind of expression we have. Gn is the G factor there, E is the charge of the proton, mass of the proton here. Okay. Now, such nuclei actually act as tiny bar magnets. That means, these nuclei which are spinning have a magnetic moment. Such nuclei act as tiny bar magnets, and these tiny bar magnets, if I take a sample of such a material, then all these kind of tiny bar magnets are randomly oriented. Now comes our magnetic part of it, that is, if I apply magnetic field to this, these spins now start aligning themselves. They align either with the field or against the field, and these two orientations kind of correspond to two different energies there. That means, basically we have applied the magnetic field. In the presence of magnetic field only, we are able to create two nuclear spin states there. One is the alpha spin state, one is the beta spin state. Alpha is lower energy, beta is higher energy, and this is the energy separation between the two. We talked about all these things in the previous session, and this corresponds to a certain frequency which falls in the radio frequency range. And if I provide that radio frequency, that means what you can have is the nuclear spin in the lower state, if given energy in the radio frequency range, gets excited to a high energy state, which is beta state, and such a transition is referred to as spin flip. So, that is all what we talked about in the previous session. Now, let us move further and see that what else happens if I put my material into a magnetic field. One is that we are getting two energy levels there. The second thing which comes up is what is called as a nuclear precessional motion. Let us understand this. This is a very important phenomenon, a very crucial phenomenon for magnetic resonance to be understood. What basically happens is that nucleus which is spinning here has a magnetic moment. This magnetic moment it does not just only spin, it starts precessing as well, because what happens is that the magnetic moment vector, which is at an angle, certain angle theta, with respect to the applied field, that means this is my applied field B naught here, and what you have is this tiny magnet I am talking about is oriented at angles, some angle over there. So, it is spinning at that angle. Also what happens is, besides this is my direction of the field here, the upward direction, the V naught. Now, my nucleus is spinning like this somewhere here at a certain angle with this. Besides spinning, it starts executing this kind of a motion. This is called as precessional motion. That means the nucleus is spinning on its own axis and also around the direction of the applied field over there. So, this second kind of motion I am talking about is referred to as a precessional motion, and it is also actually it is called as Lamar's precession. It is just to honor the Lamar. Okay. Now, let us see it a different perspective of the same. But it means if we want to see it in the macroscopic domain, probably a spinning top is the best analogy over there, because we have seen a spinning top. The spinning top spins on its axis, because we got there is a top here, there is a nail, it is spinning on its own nail. That's how axis there. Besides that, if it is just, if you just see a spinning top, it spins on its axis. Okay, but if you just tip it a little, what it starts is it keeps spinning like this. Also, it starts precessing around this motion. So, that is exactly same thing what happens in case of a nucleus there. So, that is called as a Lamar's precession. Now, another important thing here is that this precession frequency, that means the frequency at which this is getting precessing around the applied field direction, happens to be proportional to the applied field. Higher the field, more the Lamar precession frequency. And that is how we can look at it. That means the precession frequency omega is equal to gamma is gyromagnetic ratio, and B naught is a field over there. And if I just want to do a little more simplification, we can get a very important kind of an expression over here. That is, if I want to find out the normal frequency nu and the precession frequency, the kind of relationship between the two, we find that omega, that is a rotational frequency or precession frequency, is 2 pi nu. That is what we know from our basic physics, and this is given to be equal to gamma B naught. So, what we do is we just rearrange a little. So, we find that nu, that is the frequency here, will be equal to gamma by 2 pi B naught, and gamma we know is mu by I, that we have done earlier. So, if I just substitute the expression for mu and also for I, what do I get? I get the following thing here. That means, I get the frequency to be equal to G n mu n B naught H. Now, what does it mean? This is a very crucial expression for us, because this frequency, this is the Lamar frequency here, is same as the frequency of radiation required to cause a transition between the two nucleus spin states. That is what we did in the previous session. That means, we got two energy levels. This delta E corresponds to a radio frequency, and we realized that we had the same expression for that frequency which is required for this transition to be done, for the spin flip to be done. So, what you see is there are two things. One, we need a radio frequency to cause a transition, and secondly, we got a nuclear precession which has a frequency which is again proportional to the field and has a same expression there. And these two being equal actually provide us a mechanism for this to happen, for a mechanism for the resonance to be achieved. Let us see that. Before we proceed further, let us have a look at what do we mean by spin flip. What we mean by spin flip is that now this is a representation of a nuclear spin which is precessing around the applied field direction, and it is tipped at a certain angle over there, and this is aligned with the field. So, it is of low energy. I give radio frequency, the energy is absorbed, and then what happens is this spin which is aligned with the field aligns against the field, and this actually is of higher energy there. So, this is tipping of this. Okay. So, this is referred to as spin flip, and in terms of energetics, if we want to see, that is how do we represent that. That is, you have applied field beta naught over there, you got a spin aligned with this having energy equal to let's of alpha level there. I give a radio frequency to that, it flips over. So, what I get is this is my transition here, and that is delta E required over there. The nu will be equal to the same frequency we just worked out. Now, the question is, how do we achieve this kind of a spin flip? What is the mechanism? How does it happen that we provide radio frequency and it is absorbed by the nucleus and spin flip takes place? But before we come to that, let us take up one more issue here, that is we have got two energy levels there, and then we got a certain kind of collection of nuclear spins are there. So, these spins will be distributed amongst these energy levels according to Boltzmann law, that we all know of, and accordingly we know that from Boltzmann law N2 by N1, that is N2 is the population of the upper level and N1 happens to be that of the lower level, is equal to e raised to power minus delta E by kT, where delta E happens to be the difference in energy levels there, that delta E value, and K is the Boltzmann constant, T is absolute temperature. Now, why I am talking about this, it has a very pertinent or very relevant thing over there, that is, if I try to work out this as I just mentioned, delta E is the energy difference and K is the Boltzmann constant. If I try to do it for, let me take an example here. Let me take an example, say if I want to compute the N2 by N1 ratio for protons in a magnetic field of about 1.5 Tesla, which is a typical field what we use at room temperature of 300 K. If I do that, we know that first what we do is we try to compute the delta E value there, and delta E we know, we have done that in the last episode, that is delta E is equal to Gn mu n beta naught, where Gn is the nuclear G factor and then mu n is the nuclear magneton and B naught happens to be the field strength over there. So, this is characteristic of the nucleus, which a proton which happens to have a value of 5.585. This is what we worked out, the magnitude of mu n, we substitute that, then substitute the value of beta naught to be 1.5 Tesla, simplify it, what you get is this. So, that is the energy. So, this is very, very important. What you see is that the difference in energy levels is very, very small. It is about 10 to the minus 26 joules, which is tremendously small delta E value. Now, if I just go further and just try to work out, since delta E by kT is very small for this particular case I am talking about, we can use a little mathematics here and simplify this expression, that delta E raised to power minus delta E by kT can be approximated to be equal to 1 minus delta E by kT. This is true only if this exponent happens to be very small, which is true in this case. Okay. When I do that and try to compute the values, I find that N2 by N1, the ratio of N2 to N1 comes out to be 0.99998898 and so on and so forth. What does it mean is, it means that for every 10 to the power 5 spins in the lower level, that is about 1 lakh of them, 100,000, there are 99,999 spins in the upper level there. That means there is only difference of 1 nuclear spin in 10 to the power 5, which is a very, very small difference there. Though this difference is small, but with the number of molecules we deal with, which happens to be in trillions, this difference becomes reasonably okay. But all said and done, the implication of this is that NMR spectra are intrinsically very, very weak. Okay. Now let us go further and see what is the meaning of resonance in case of NMR. Let us understand that. Now, in order to understand resonance, let us see what basically has happened here. That means, I have taken a sample, put into a magnetic field. When I put into magnetic field, different nuclear spins, they distribute among themselves amongst the energy levels there, according to Boltzmann distribution, as we just discussed there. So, as a consequence of that, what will happen will be that there will be more spins which will be aligned with the field, and there will be lesser spins which will be aligned against the field. So, it has been just schematically shown over there. Since there are more spins which are aligned with the field, what you will have is, you will have a net magnetization in the direction aligned with the field there. This is my z direction, is my field direction there, that is B naught here. So, there will be net magnetization in the direction of the field there. So, that is the consequence of distribution of the spins amongst the energy levels there. Now, but our issue is that we want to kind of execute a transition there. So, in order to do a transition there, we need to supply energy, and that energy we know is supplied in terms of a radio frequency there, and that radio frequency actually is applied along the x axis there. Our nuclear spins are aligned, that means there is a net magnetization which is given as m naught in the direction of B naught or the z direction there, and I apply radio frequency along the x axis there. A radio frequency basically is an EM radiation. EM radiation, we know that there is an electrical component there, there is a magnetic component there. So, out of the two component, it is the magnetic component which is of interest to us there. So, we have got a oscillatory magnetic field which is coming there. So, that oscillatory magnetic field has to interact with this kind of a spin magnetization which is aligned with the field over there. Now, how does that happen? In order to understand how does that happen, we have to see that this radio frequency we are talking about, because this oscillatory field, this in fact can be seen as made up of two counter rotating components. That means, this oscillatory field here can be thought of to be made up of two rotatory fields there. Let us understand this. Now, suppose I have this as my kind of say a magnetic vector there, say of the EM radiation there. Now, we know that when talking about oscillation there, say this magnetic vector is here, it decreases, 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 comes there, becomes negative, then it oscillates like this. So, that is what you are trying to look at there. Now, same thing can be achieved by thinking of two counter rotating components. Let us understand that. What it means is, let me think of this vector which is moving clockwise like this. Another vector is moving anti-clockwise. So, there are two things there. Now, suppose there are two things, both are aligned. So, net is the double of that. Now, suppose these two vectors, one moving clockwise, one moving anti-clockwise, they go at the same speeds. This moves like this moves like this. Now, if I try to take these two vectors and try to find out the resultant of that, that will be lesser than the sum of the two, that will be shorter vector there. Let it continue further. When the two becomes like this, diagonally opposite to each other, the net will be 0. When they go downwards there, it will become negative and all. So, what basically happens is, when the two vectors of the kind of circularly rotating components there, or rotating component as they are called. So, when they move counterclockwise, one is clockwise, one is anti-clockwise, we find that this vector to begin with was much larger here. When the two vectors, the one is kind of rotating clockwise, one is anti-clockwise, the net is somewhere here. When they come opposite to each other, it will be 0. When they become like this, the net is like this, and then when the two align again in this direction, we find it becomes so much there. So, essentially, if I look at only the resultant of vector there, so resultant vector is very large here, becomes smaller, becomes 0 here, somewhere we should have had a figure here which says is 0, or then it becomes negative like this, or it becomes further like this. So, what you see is that this is an oscillatory field over there. So, there are two ways of doing that. One is basically I am trying to look at a magnetic field which is oscillating, and that can be represented in terms of, or resolved in terms of, counter rotating components there. That is important. Now, what happens then? What happens then is that these rotating components will depend on the frequency of the radiation I am talking about there. Okay. Now, let us see here what happens. What happens is, we have a net magnetization vector here, which is precessing at a certain frequency depending on the applied field there. Then what do? I provide a radio frequency. Radio frequency, say let me assume I am taking some arbitrary units here. Let us say this is precessing at some 100 units over there, okay, and I am applying a kind of radio frequency along x axis, and say the frequency happens to be say 97. So, if it is 97, the circular component along this axis, this direction here, which will be having a frequency of 97 units there. Increase it further, make it 98, 99, nothing happens, no energy absorption is there. The moment this radio frequency becomes 100 units, similar to this frequency over there, these two resonate and there is an energy absorption. That is the meaning of resonance there. That means, resonance will come into picture only when the precessional frequency and the radio frequency, the two exactly match. When the two match, there is spin flip, or what you in kind of a, in terms of a gross aspect of it, what basically we show it as that this net magnetization vector which was pointing in the z direction gets tipped like this, because now what will happen is some more spins which were aligned now becomes against there. So, if you remember the previous figure, what we talked about was there were many more spins aligned with the field than which were against the field. Now, because of this transition here, now we find that the difference becomes lesser here. So, that is the kind of excitation we have, and in terms of net magnetization, this vector has got tipped towards the y axis there, and this tipped vector actually, the y component of that actually is measured there. So, what you have is, there are three things there. You have got a field along z axis, which is my B naught here. You give energy from x axis, that is my radio frequency, and along the y component you have a receiver here which will measure the outcome of that. So, that means the resonance signal, that means how much of energy has been absorbed, how many spins have got flipped over, that is measured by the y component of that. So, that is more of the instrumentation part of it, we will not get to that, but our concern here is to understand the concept part of it, what is the meaning of resonance here. So, resonance for us is that stage at which the frequency of the applied radio frequency, that means the circular component of that, and the precession frequency, the two match exactly. At that stage, the resonance comes into picture there. Okay, let's move further. So what will happen if I keep on giving radio frequency? What will happen? What will happen is that we had more spins aligned with the field, lesser were against. I gave energy, so these spins which are aligned have become against the field. So this difference is decreasing, and if I keep giving radio frequency, a stage will come when the population of both the levels become equal. That is referred to as saturation of the excited state. Now, if that so happens, that means if the population becomes equal in both the levels, there is no absorption and nothing will happen thereafter. But fortunately for us, that does not stay as such. When we give radio frequency, the difference in population does decrease, become lesser and lesser. They tend to saturate, but there are certain mechanisms which come into play, which let this balance to be maintained. They are called as relaxation mechanisms. That means there are nuclear spins, they relax to maintain this population difference, and there are two such mechanisms for that. Let's quickly look at those two mechanisms there. One is called as spin-lattice relaxation, the other one is called as spin-spin relaxation. Let's look at this, very simple ones there. Now, spin-lattice relaxation, as the name suggests, basically this involves the transfer of energy from the nuclear spin in the higher energy state to the molecular lattice. So, what it means is this: you have got a nuclear spins which have got excited now. So, they have got high energy. So, they will tend to come down in energy, and that coming down in energy happens because this nuclear spin is not in isolation, it is in a system there, it is in a solution there. So, there will be a molecular lattice around that, maybe of solvent or other molecules there. So, the energy of the spin is transferred to that, and as a consequence the spin loses energy and comes down to the ground state here. This is called as spin lattice relaxation, also called as longitudinal relaxation. Now, this longitudinal relaxation actually helps in maintaining the excess of population in the lower energy level, because population difference has become less now because the spins are getting relaxed down to the ground level. So, this population difference is maintained over there. So, relaxation actually leads to recovery of the Z component there. What it meant was that you have a net magnetization in the Z direction there. I give radio frequency there, some of the spins which are aligned with the field now go against the field. So, this vector tips off, and when this is tipping off because there is an excitation there, and when the spins go back to ground state, so this will be recovering back to this. That is the meaning of recovery here. And then this recovery actually is characterized in terms of what is called as a spin lattice relaxation time. This is a very, very crucial parameter in the context of NMR, which probably will not be using much of it, but we need to understand what this is the important thing there, because this is what is going to determine the way NMR spectrum looks like. Okay. The second kind of relaxation is termed as spin-spin relaxation. As the name suggests, spin-spin. That means this involves mutual exchange of spins by two precessing nuclei in close proximity of each other. What it means is this one spin there which is in excited state has high energy, you got a neighboring spin which does not have high energy, it is in the ground state there. There can be a transfer of energy from here to here. So, and this might get excited, this will come down there. So, that is called as spin-spin relaxation, and also referred to as transverse relaxation, and this basically decreases the half-life of the excited state, because if the spin which has got excited gives energy to someone else and comes down, so the lifetime which is spent over there decreases there. That is a consequence of spin-spin relaxation, and this is actually characterized by a spin-spin relaxation time T2, that is called as T1, spin lattice relaxation time is called as T1, and spin-spin relaxation time is called as T2. Now, let us sum up what we have done today. What we have done today is we briefly reviewed the contents of the previous session, where we talked about the fundamental aspects of this. Thereafter, we explained the meaning of resonance in the context of NMR spectroscopy, because that was very, very crucial for us, because we had covered nuclear and magnetic component there. Even before even coming to this, the meaning of resonance, we did talk about the precessional motion, and also we talked about that the distribution of spins amongst the energy levels there. And thereafter, we explained two important relaxation phenomena, that is spin lattice relaxation and spin-spin relaxation, and their importance, because they are the ones which are very, very important phenomenon, particularly in terms of their being able to maintain the the population difference there, so that the energy absorption can take place and we can get a meaningful spectrum there. I am sure that by now we know what is NMR as a phenomenon, and in the next session we will talk about that how do we actually run a NMR spectrum, how do we kind of measure the NMR spectrum for a given sample there. So, all that and what kind of information we get from there, that shall be taken up in the next sessions. Thank you so much.